right, well, thank you. I really appreciate y'all coming. Thank you for the introduction. I really appreciate it. My name is Charles Adams. I'm a professor of history here, social science chair here at NCTC. Been doing this for a long time. Love it. This is where I'm retiring, so I must be doing something right. And like in the introduction, I was prior to this an engineer. I worked in counterterrorism for over a decade. During the War on Terror, during 9/11, actually it was a bad day to be in counterterrorism. And just decided after life events and a heart attack that I would take a vow of poverty and become a historian. And it worked, of course. So, but I've never been happier and I've never been more relaxed in my life. So, because of my background, being born in Los Alamos, which we'll talk about today, this is the reason why I can read at night with the lights off. My father was a nuclear engineer. He worked in nuclear safeguards. Spent his entire career trying to find ways to handle nuclear material safely. So I've always been kind of had a fascination with this process for making the atomic bomb. I'm going to give 2 words of warning here as we go through this today. It is a historical lecture, but it gets a little bit sciencey because I'm a former engineer and I geek out on that. I really enjoy it. I went through it and I tried to take some of the stuff down, not to get too crazy, and some of the stuff I did pull back. We're not going to do equations unless you want to. But I do have just the general science behind it. Today is July 16th, 2025. 80 years ago today, at a set of lava fields called Jornada de Muerto, Day of the Dead, at the Alamogordo Gunnery Range, which was approximately at the time about 60 miles north of Alamogordo. It's not in Alamogordo. And about 5:30 in the morning, we did this. This is what is known as the Trinity shot. This is the first ever atomic bomb. The first time that we've ever utilized the atom in such a way to create an uncontrolled chain reaction which released a tremendous amount of energy and changed the world forever. Right? Now, the question that I'm posing as we are beginning to kind of explore this historically is, first and foremost, is how did we get there? How did we even get to this point where we thought, oh, we can harness this kind of energy, right? Well, the story actually begins in 450 BCE. That's a long time ago. And it begins with this guy, Democritus, a philosopher, Greek philosopher, right? We all love the Greeks. And in 450 BCE, Democritus had a question. Somebody was pondering. He's like, if I take an apple and I cut it in half, and then I cut it in half again, and then I cut it in half, and I keep doing this, I keep cutting it in half. At some point, I can't cut it in half anymore. Is there a point when I have something that I can no longer cut it in half, and then what is it? And so he decided to call that state when you can no longer cut things in half. He called them atomos. Atomos is a Greek adjective that literally means uncuttable. Right? And this is where we get the word atom from. It's from this Greek word atomos. So you think, okay, well, way back in 450 BCE, we're already on our way to understanding matter. However, about 100 years later, somebody else came along, another Greek philosopher, who said that Democritus is an idiot. This man doesn't know what he's talking about. The guy happened to be Aristotle. Well, who holds more clout? Obviously Aristotle, right? How many of you up to this point had not heard of this guy, but had heard of Aristotle? Okay. So as a result of this, Aristotle thought this whole theory was ridiculous, that there was the 4 elements, that's it, right? Earth, wind, and fire. No, wait, that's the rock. Earth, air, fire, water, right? You have the 4 elements. And basically this whole idea of having the uncuttable atomos decided to be shelved, pushed aside for the next 2,000 years. Well, fortunately, time does march on. And in the 1600s, we do get the return of the atom. During the Renaissance, during this time, we're going to start seeing this idea of this indivisible particle begin to come back. And it's began in the 1660s with a philosopher by the name of Robert Boyle. He's going to challenge this Aristotelian idea of the substance only consisting of those four elements, right? Earth, air, fire, and water. And he's also going to challenge the Paracelsian idea that there's only three elements, which were salt, sulfur, and mercury, which is even more limited, right? And he's basically going to say both these guys are not right. And he's going to begin to promote this idea of elements, right? This is a corpuscularianism idea that theorizes that all matter is made up of little tiny particles that are in constant motion. Everything about us is made up of these little tiny particles. Now, in the early 1700s, Isaac Newton is going to take this idea that Robert Boyle presents, and he's going to run with it. In 1704, he's going to publish a writing called Optics, a book called Optics, in which he's going to theorize that God had created matter as small spheres that are indestructible and innate with predictable properties that are surrounded by the principles of attraction and repulsion. Now, if you know anything about Isaac Newton, you can see why he has this slant on this. Because ultimately what he is most interested in is what is these forces of nature, right? Remember we talked about things like gravity. And from this we get the concept of the physics concept of Newtonian physics. Beginning in the 19th century, the idea of atomism would finally take hold thanks to the theories of John Dalton. John Dalton would write a book called New Systems of Chemical Philosophy. And in this, which was published in 1807, so we're in the 19th century now, he introduced the idea that not only were there definable elements, but that these elements combine in only fixed proportions. Basically, he had three principles that he put forth in this writing. First was, all substances are made of atoms, which are the smallest particles, and cannot be divided, they cannot be created, and they cannot be destroyed. The second principle was that all atoms of the same element have the same mass. So if an element has a different mass, it's not the same element. And finally, atoms join together in compounds that are always consist of the same kind of atoms in consistent ratios. Basically, what he is touching on here is this concept of molecular structures. All right, so now we have atoms. We got them back. But they're still indivisible, indestructible. We can't create them. We can't destroy them. Until we can. Until we can start thinking about this. Right? Now, the concept of atoms was very readily accepted in the field of chemistry. Physics, not so much. There was a little bit more resistance to that, right? But by the 19th century, it was generally accepted that you had these. In 1896, though, we're going to start to see some people theorizing that maybe there's more to these atoms than just being little tiny indestructible things. And it begins with research in radioactivity. Specifically, in 1896, a French physicist by the name of Henri Becquerel is going to begin playing around with some uranium salt that he was left that was left to him by his father when he died, which is a darn strange thing for your dad to leave you in a will. My father was a nuclear physicist. I got a spoon collection. Not nearly as interesting. This guy gets uranium salts. I really feel a little bit robbed on that. But he discovered that by using when he had these uranium salts near photographic film that would cloud it. And so he began to theorize, why is this happening? What is going on that's making this happen? And he determined that there was some form of natural radioactivity that was causing this. Now, his theories were built on by a name you probably do recognize, Marie Curie and her husband, Pierre Curie. Marie Curie was a Polish-born physicist, had a very illustrious career in the field. Matter of fact, if you take a look at a couple of the elements out there, polonium, it's named after her home country, Poland, and radium, she also named that one, and ultimately her research in it killed her. But Marie Curie and her husband built upon this work on natural radioactivity in elements that was pioneered by Becquerel. And as a result of this, by 1903, the three of them collectively all shared the Nobel Prize in Physics due to their research. Now, if we have these indestructible, indivisible atoms are emitting some kind of radiation, maybe they're not indestructible, and maybe they're not indivisible, and maybe they're not the smallest part. So people began to look even further. In 1897, a British physicist by the name of J.J. Thomson is going to announce that through his experiments through electrical charge, he determined that it was clear that atoms had some minute particle that would orbit around it that created the electrical charge, right? As a result of this, he called these little particles that he theorized orbited and transferred back and forth between matter and called them electrons. In 1911, a New Zealand physicist by the name of Ernest Rutherford is going to take it to the next step. He's going to take a look at the atom. He says, you know, the atom is actually made up of void space. There's not a whole lot to it. It's got a very tiny, tight core that has those electrons that J.J. Thomson established existed orbiting around them. And that tight core was made up of positively charged particles called protons. Okay, so we've got protons and electrons now. Now we're on our way. Matter of fact, we're really only missing one thing. Now, the person you see pictured here, I don't have his name on here, this is Niels Bohr. He was a Danish physicist and one of the most famous physicists of the 20th century. He's going to take these ideas of Rutherford and Thomson, and he's actually going to create the first model. His theory was that if you have these protons that are positively charged and electrons that are negatively charged, that they will offset each other like two magnets, and they'll rotate around each other just like the planets do around the sun. And so he came up with the first physical model that used hydrogen. Why? Because it's easy. Right? One proton, one electron. And he came up with the first model of it. Now, the last piece of this puzzle doesn't get discovered until 1932. And that was by a physicist that worked at Cambridge with Rutherford by the name of James Chadwick. He said there was more than just protons in that little tiny core. There was a bunch of material that also had no charge, not positive or negative. So if it's not positive or negative, it's neutral, so we call them neutrons. There we go. We have all the pieces in place. And now this indivisible atom that we've been talking about has got all these parts. Well, as you all remember when you're kids, if something has parts, you can take it apart, right? Doesn't mean you can put it back together, as we often found, but we can take them apart. Now, in order to explore how this might happen, we're going to change gears a little bit. And we're going to think about two interesting questions that took place in the physics world here in the early 1900s that ultimately will lead to people being able to theorize how you can take them apart and what's going to be the result if you do. And we're going to begin with the special theory of relativity and, of course, our boy Albert Einstein. Albert Einstein was a mail clerk and a physics graduate, and in the early 1900s he was pondering two seemingly unrelated but interesting theoretical questions. One was, if a light wave is traveling, and I can run as fast as it's going, I can run at the speed of light, and I look over at this light wave, what would I see? The second question he was asking is, if I was going the speed of light and I held a mirror up, would the mirror go dark? Would the light be able to reflect off my face, off the mirror, and back to me? And from these two questions he was asking himself, he came up with a theory of what was known as the special theory of relativity. Now, there's three main points of this. Two of them are kind of uninteresting for our discussion, at least on the atomic bomb, but one is really important. The three things he poses in this paper that he published on it called on the Electrodynamics of Moving Bodies, which is a typical title for something written by a physicist, which is why they don't like romance novels. But in this, he said, first of all, this theory that there is an ether is bunk. There was actually a belief that the only reason that light waves could move at all is it had to move through something. Everything else does. Sound moves through air, right? So how does light move through space? Well, there must be something there, and we call it the ether. So no, that doesn't exist. It's not real. The second thing he stated in this was that the laws of physics are the same for all observers in uniform motion. How does that throw things on its head? Well, I mean, think about it a minute. If I'm on a rail car right now going 10 miles per hour, and I'm walking 3 miles per hour along with it, how fast to you does it look like I'm going? 13 miles per hour. And he's saying the rules of physics applies to everything, regardless, provided they're in uniform motion. And the third thing he came from, this is the important one, is that the speed of light is fixed. Because the thing they found out is that it didn't matter if you were on the rail car or not, the speed of light was still the speed of light, 186,000 miles per second. Ish. Right. Always the same. So in other words, if I'm holding that mirror, will I see myself going the speed of light? Absolutely not. Because the speed of light is fixed. It doesn't matter that I'm going the speed of light. The light cannot go faster. Now, the problem with this, and the reason why it's called the special theory of relativity, is because the equations for it work great as long as everything's in uniform motion. But the moment something's speeding up or slowing down or rotating or doing something like any kind of change, the equations fall apart. Well, Einstein's not done. We're not done with him either. Because first of all, he's too photogenic. Right? Einstein, at the same time he was thinking about this special theory of relativity in 1905, he was also thinking of energy in its relationship with light. I mean, it kind of makes sense, right? He's kind of playing around with light, and light and energy are closely related. As a result of this, he's going to publish an article in the Annales der Physik called "Does the Inertia of a Body Depend Upon Its Energy Content?" See what I mean? No romance novels. It's never going to happen. Okay. Now, in this, he is building the groundwork for what will be, by 1950, become his theory of general relativity, where he ties it together where it doesn't matter if you're moving or not. Now, I'm not going to bore you with all the details of that. Ultimately, the general theory of relativity is going to consist of 10 separate equations, but only one of them is really important to us, and I bet you somebody here knows it. What is
MC squared.
There you go. And a lot of people will think, I thought that was the only one. There's 10 equations. But this is the one, but it's important. Because energy equals the mass of an object times the speed of light squared. What Einstein here is theorizing is that mass and energy are interrelated. And something if it has mass, it has a lot of energy. I mean, think about it. The mass is times the speed of light squared. Now, I already said the speed of light's pretty darn quick, right? Now square it times the mass. Put this in perspective. If I was to take a 1 kilogram object, 2.2 pounds, okay, so let's say a London broil, because I'm hungry. 2.2 pound London broil. and I was to convert it into pure energy using this equation, so I have no losses, no heat, just turn it into pure energy, I would get 9 times 10 to the 16th power joules of energy. It's like, oh no, human science, don't do that. All right, 90 quadrillion joules of energy. Put that in perspective, right? You got thousands, millions, billions, trillions, quadrillions. There you go. You know, after a while, it becomes a child's number. You know, we're almost there. We do have a name for this one. Okay, 90 quadrillion. Now, again, what does that mean? Well, if you were to power 10 million homes with that, you could do it for 3 years. If you were to convert it into something we're more familiar with, calories, it's 22 quadrillion calories, which equates to 88 trillion chocolate bars. Getting a lot out of my London broil, aren't we? That's a lot of energy. And for the sake of this talk, it would be the equivalent of a 40 megaton bomb. 40 million tons of TNT. All explosives are measured in what's called TNT equivalent. How much TNT would you need to have to make the same size boom? And when we're talking about atomic theory, we're talking in kilotons, thousands of tons of TNT, and megatons, millions of tons of TNT. 40 megatons. Best way I can put that in perspective, the largest nuclear weapon ever tested was a weapon called Tsar Bomba by the Soviets. It was in 1961, if I remember correctly, and it was because they didn't put the booster on there. They took the booster off because they were afraid it would rip a hole in the atmosphere. It was 50 to 53 megatons. So, London broil. You'll never think of that test ever same again. Those of you who teach history. So, all right, so that's what we're looking at as far as power. So now we have all the pieces in place. We have the mathematical theory on how much energy we can get. We have the knowledge now that an atom is not indivisible. So now we just got to figure out how to do it. How do we split this atom? And the initial attempts to do this, especially in the early 1930s, were met with extreme frustration. Two gentlemen, Ernest O. Lawrence and Robert J. Vandergraaf, in the 1930s, were both trying to do this. And the way they had done it is that these two men collectively together had created a thing called a particle accelerator that could accelerate these free particles. Specifically, they could accelerate protons. You can take protons and try and bombard an object with it and see if you can get that thing to split apart, get that atom to split apart. And it was frustrating. They were getting nowhere with it. Now, if you think about it, it really kind of makes sense. Have you ever had two magnets in your hand and you try and put the positive and the positive side together? It doesn't let you do it, does it? Fights you all the way. They were shooting protons with a positive charge at the center of an atom, which has a positive charge. So in their tests, they would typically get about 1 hit out of every million particles. Matter of fact, Ernest Rutherford became so frustrated with it, he called the idea of bombarding atoms with particles, he called it moonshine. Can't be done. Well, in 1934, Enrico Fermi took a different perspective on this. Right? Now remember, only 2 years prior, James Chadwick had discovered the neutron has no charge. He said, why don't we just shoot neutrons at this thing instead of protons? Well, you know, why don't we do that? And it was very effective. It was so effective, in fact, that he ended up he created things he never thought he would, and he got confused about what he was really doing and what he had really done. He bombarded 63 different types of elements, and in the process of doing it, to his amazement, he created 37 new things. And then he became obsessed with, what the hell did I just do? What is this? What have I done? Didn't even stop to think about Einstein's formula, energies, and all this kind of got lost. To his real surprise, when he did this with neutrons with uranium, the heaviest element that you can find naturally here on Earth, it not only became something else, but it became something very slightly heavier. It became something that went up the periodic table, not down. Usually, if you've got something that's going through what we call radioactive decay, it goes down. Not always. Okay? And additionally, in one of his byproducts, he was also getting other elements that were weird because they were acting like things that were clearly far lighter than uranium. What was happening here was that Enrico Fermi was splitting atoms and didn't even know he was doing it. So he had split the first atoms and just hadn't realized it. On December 21st, 1938, Otto Hahn and Fritz Strassmann are going to build on these tests and actually knowingly split an atom. The guy on the left here is Otto Hahn. The person on the right is not Fritz Strassmann. That's actually Lisa Meitner. Okay. Otto Hahn and Fritz Strassmann are going to begin bombarding uranium atoms with neutrons. And they discovered that the property of uranium had changed substantially. That the uranium had become lighter elements, and one of them they actually identified a radioactive form of barium. And as a result of that, they went, oh my God, we split this atom. This atom became two smaller atoms. But he wasn't sure. Otto Hahn wasn't sure. So he sent the results off to Professor Meitner here. She was no longer in Germany by 1938. The reason why, she was of Jewish ancestry. She had fled Germany. She was Austrian, actually, by birth. But she had fled Germany and she had moved to Sweden along with her cousin Otto Frisch. But Otto Hahn, who still kept in contact with her, sent her all of his test results and basically said, what did I do? We did something. Did I split an atom? Her and her nephew, Otto Frisch, went through the data and said, yeah, we can confirm that you split the atom. And it's Otto Frisch that's going to come up with what we should call this. Otto Frisch was really into biology, botany. And so he thought, well, you know, when cells divide, we call that fission. So we'll just call this the same thing. We'll call it nuclear fission. Now, this is problematic. Think about who Otto Hahn is. Otto Hahn is the director of the Kaiser Wilhelm Institute of Chemistry in Berlin in 1938. Yeah, it's a little scary, isn't it? And a matter of fact, as a result of these tests and confirming this, which the entire physics world was abuzz about, this is just before the veil of secrecy begins to descend down on all of this stuff. Adolf Hitler was very happy to appoint Otto Hahn the head of the Nazi atomic bomb program. Because what they had realized in the process of doing this is that not only would the atom split, but every time it did it, it was shooting out additional neutrons. And those additional neutrons, if they go and they hit another atom and split that, well then that will release even more neutrons. And they'll go out and split some more, and you can create what we call a chain reaction. Now, if you've got that under control, that's incredible, right? Think about the power you get out of this. Remember, all this energy, E equals mc squared. Right? That you're getting out of this. But there's a downside to that as well. What is the difference between a fire and an explosion? Control. Speed. Right? A fire is a chemical reaction, right? An explosion is a fire, is just really, really, really fast. It's just using all the material all at once. Well, now we have the ability to split an atom, it releases a lot of energy. If we can control it, it's a chain reaction that we can get a lot of use out of, a lot of energy. But what if it's a chain reaction happening really, 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 really fast? Now you have a bomb of unspeakable power. People are, needless to say, very frightened by this. especially when you consider what's going on in Nazi Germany. Nazi Germany technically now has the lead in the race for the atomic bomb, despite the fact that because the Nazis were in power, that Germany was losing a lot of their best scientists. A whole list of scientists that were either from Germany or from allies of Germany had fled to Britain, the United States, Sweden, elsewhere, right, in order to escape Nazi tyranny. These might here that we mentioned: John von Neumann, Edward Teller, Leo Szilard, Eugene Wigner, James Franck, Max Born, and of course Albert Einstein. Right? He actually renounced his German citizenship twice in his lifetime. It was so nice he did it twice. Okay. Now, Leo Szilard was a Hungarian physicist who had fled to the United States along with Edward Teller. Edward Teller, if you're not familiar with who he is, he's ultimately going to be called the father of thermonuclear weapons, the hydrogen bomb. Something we won't have. Szilard became so concerned with this, he thought, you know what, we cannot let the Nazis get the bomb first. We have to have it. In order to do that, I need to write a letter. I'm going to write a letter from Albert Einstein to Franklin Roosevelt. How would you do that? Well, I'm going to put it this way. 1938, 1939. Who's heard of Leo Szilard? Remember, we asked that question. How many of you have heard of him before tonight? Okay. How many of you have heard of Albert Einstein? Okay. Same's true back then. Szilard has no assumptions. He knows he's not some hotshot. He's not famous. If he writes a letter to Franklin Roosevelt saying, hey, the Nazis are going to get the bomb first, and we need to exercise all we can to make sure that we have a program to beat them to it, Roosevelt's going to go, who knows this guy? I don't know who he is. But if it's from Albert Einstein. So he wrote a letter from Albert Einstein. And all he has to do is get Einstein to sign it. There's only one problem. He can't get to Albert Einstein. It's too far to walk. Leo Szilard does not know how to drive a car. So what does he do? He recruits his Hungarian compatriot, Edward Teller. Edward Teller would later go on, he would actually later tell me, I got to meet him in 1999, when he talks about the Einstein letter, he says, that day I was not a physicist, I was a chauffeur. As he loaded Szilard into the car and drove him up to Einstein's house to tell him, you've got to sign this letter. And on August 2nd, 1939, Einstein is going to sign this letter, known famously as the Einstein letter. Sometimes it's more appropriately called the Einstein-Szilard letter, which would make more sense since, like I said, pretty much he wrote it. There were some edits that were done after they got together, so it's very minimal. Right? And basically what it said was that we needed to develop this weapon for the Nazis. They sent it off to Roosevelt, and Roosevelt looked at it in October. So even with Einstein's name on it, it didn't even get viewed until October of 1939. And Roosevelt felt, this sounds expensive. This sounds like it's going to cost a lot of money. I don't know if we want to do this. And he was really considering just absolutely walking away from this idea altogether. Fortunately for us, one of his friends and advisors, a guy by the name of Alexander Sachs, took a look at that and said, no, I think we really need to get behind that. And on the 19th of October, 1939, Roosevelt wrote Einstein back saying, yes, we will set up a committee to begin looking at a program to try and beat the Nazis to this new weapon. So, by this point, we have established that we can take uranium, we can potentially split it, we can possibly make an atomic bomb. It's not actually as simple as that. Science time again, sorry. Right? Not all uranium's created equal. Not all uranium wants to split. Some of it's perfectly happy to be what it is. Or it wants to change, but it doesn't want to do it fast. Fission? No, that sounds dangerous. I'll just decay. Just like most other radioactive isotopes, right? The most common form of uranium is uranium-238. About 98% of all uranium is uranium-238, and unfortunately, it is the one that does not like to decay, or does not like to fission, sorry. It would rather just decay and actually become something else, which we'll talk about in a little bit. Okay? But uranium-235, sometimes you leave it alone, it'll fission by itself. If it collects a proton, it becomes uranium-236, bam, it happens. Something about even numbers they don't like. I don't like them either, so I'm on their side. So the question is how do you separate that? I mean, think about this for a minute. If I was to give one of you 10,000 pennies and tell you, I want you to separate just the ones that are from 1960, which you can't look at the date. But every one of those pennies from 1960 is 1% lighter than the other pennies. How do you feel about separating those? Sounds pretty awful, doesn't it? How do you do this? That's something they got to figure out. They know they want this uranium-235, but how do you separate uranium from uranium? It'd be so much easier if they were just different elements, right? You just do it chemically. I can separate hydrogen and oxygen from each other, right? Take water and turn it into hydrogen gas and oxygen. I can do that chemically. Can't do that with uranium. So they began to kind of pose ideas. How are we going to make this happen? How are we going to get this done? They come up with 4 different ideas. 3 of them they'll do. The first one is actually the one that is most commonly used. This is the one that you see in the news today when you take a look at, like, for example, the Iranian enrichment program. High-speed centrifuges. You spin something really, really, really fast. The heavier stuff goes to the bottom first. You take the lighter stuff off the top. When you do that, you now have the 235 and still a lot of 238. So what do? You send it to the next cyclotron centrifuge, and you spin it again, and you just keep doing that, and you keep doing that, and you keep doing that. It gets more and more enriched, more and more, until you finally hit that amount you need in order to make a successful atomic bomb, which is about 80% 235. Okay. The Manhattan Project is going to abandon this. The technology had already been done. Matter of fact, Jesse Beams had been doing it since 1934. He was using it to separate chlorine-35 from chlorine-37. Same kind of thing, right? He's trying to separate needles and needles, trying to find the same needle and the same haystack with one's 2 neutrons heavier. Okay. But the problem with this is, first of all, for uranium, the speed was insanely high, at least 50,000 RPM. And the equipment, the bearings, the technology was such that these things had a tendency to a lot of energy, and they tended to break down. And usually when they broke down, especially to a bearing failing, they broke down catastrophically. It's one thing about, it's just, when it comes apart, it comes fully apart, right? When the bearing fails. So this one got abandoned, at least during the Manhattan Project. Like I said, it won't make it come back. The next one that they'll try, this one they'll go ahead and develop a plant to use, is electromagnetic separation. In order to separate uranium in the first place, you've got to turn it into a gas. The only gas that uranium readily turns into is a thing called uranium hexafluoride. It's a very ionized gas, which means if you pass it through a magnetic field, it will bend. Any ionized gas will bend in a magnetic field. The heavier it is, the less it bends. The lighter it is, the more it bends. You put enough charge on it, you can literally make it go in a circle. So, what do? You take this uranium hexafluoride, you run it through an electromagnet, and the stuff that bends the most is the stuff you're collecting. The rest of that stuff, you're letting it just pass on by, you're pulling the 235 out of there. And again, you have to do it over and over and over again. So, they did this. They did this in Oak Ridge, Tennessee. They called it the Y12 plant. But they weren't done yet. It's like, we're not going to just do one way. We don't know which one's going to work the best, so we're going to keep on rolling. They thought, well, what if we tried gaseous diffusion, right? If we run things through a strainer, the smaller stuff goes through first. Right? Now we're talking about gases and molecules. You can imagine this is more than just the, cheesecloth. This is finer than that. But still, that's exactly what they're going to do. They're going to run this stuff pressurized through a filter. The 235 goes first. A lot of 238 goes through as well. But then you move it to the next one, and you do this over and over and over and over and over again until finally you get the enrichment we want. We're going to do that. It's going to be called, again, in Oak Ridge, Tennessee, it's going to be called the K25 plant. This is literally going to be these diffusions going all the way here, all the way down, across here, all the way back up. I don't want my offices against this backbone. That's all I got to say. Right? So we got that technique that we're going to use. Okay? And then finally, because we're not done yet, it's got one more we're going to try. What about thermal liquid diffusion? We'll use thermodynamics. If we run this hexafluoride through a pipe and have cold water as the outer jet, basically you got a pipe within a pipe within a pipe. The inner pipe has hot water. The furthest outer pipe has cold water, and the pipe in the center has the uranium hexafluoride. The lighter stuff is going to, through thermal diffusion, gravitate towards the hotter heat source. And so then you just siphon that off. And we'll call that the S50 plant. So we got 3 crazy ways to try and separate uranium from uranium. Now, I said of these 4 different techniques, the 3 that we end up using, we don't really use it. So from that, we're going to start developing and producing uranium-235 in order to make weapons-grade uranium that we use for the bomb. But remember, the Manhattan Project is all over the United States. There's a whole bunch of different things going on. This is the second most expensive project in World War II. The only thing that costs more than the Manhattan Project is the project to develop the B-29 bomber, which actually was used to deliver the atomic bomb. So you can technically roll that cost in if you want. Right? So, in Chicago, Enrique Fermi, along with help of Dios Solar, are going to work on a different concept. Can we create just a sustained controlled chain reaction using just regular uranium, using 238? In order to do that, first thing we got to do is we got to order a whole bunch of carbon, a bunch of graphite. In February 1940, Enrique Fermi told the government that he needed 4 tons of graphite, 50 tons of uranium oxide, and he needed tubing and wiring for all this, but copper was a commodity during World War II. And so he asked the Treasury Department for about 12 tons of silver, which I'm sure went over really good. We're just going to borrow it. We'll give it back. You may not want to touch it, but we'll let you have that. Right, so they developed, the idea between this is graphite is going to do something. Here's a little something about splitting an atom. Again, a little science here. If the neutron's going too fast, it won't split the atom. We all have this idea in our heads that the way the atom splits is the neutron hits it so hard that, bam, blows it in two. That's not how it works. It absorbs the neutron and becomes wickedly unstable and breaks. That's what fission is. So if it's going too fast, it literally just kind of flies by it. Imagine this. Imagine you're lining up for a putt. The hole's right there, and you hit it like you're hitting a driver. And that ball slides right over the hole. So you got to slow them down. One great way the best way to do it is hydrogen, because what you basically want is a neutron. It's about the same size as hydrogen. Imagine if I had these 2 things hanging from a string. If I hit the golf ball to a golf ball, to use that as an example, that's going to stop, this is going to go, right? This is my neutron, I stop it. Carbon's a little bigger, so I get a little bit of a reaction, but I've slowed it down. It's like a golf ball bouncing into a tennis ball. Right? If you want to try that experiment. So you slow it down so it gets captured by this uranium-238. Uranium-239, when it captures 1 neutron, not a big deal. Uranium-240, remember, oh, I don't like that. And uranium-240 will almost immediately decay. What does it do? One of the neutrons in it decides, I don't want to be a neutron no more. I don't like that, I want to stand out. So what does it do? It spits out an electron and an antineutrino, we won't talk about it. And becomes a proton. So now your uranium, atomic number 92, has just become neptunium 93 on the scale. These guys are using graphite at Stagg's Field at the University of Chicago to try and see what they can do with this uranium-238. And what they're doing is they're creating neptunium. Neptunium, though, is even worse. It actually will go find a neutron. You don't have to shoot one at it. It'll just go like that. It grabs one. That one immediately goes, well, I don't want to be a neutron anymore either. And it becomes plutonium. So by using a graphite moderator to slow the neutrons down, CP1, which was done, this is literally built, it's a carbon pile, CP literally stands for carbon pile, that was built in a squash court underneath the stands at the football stadium at the University of Chicago. I don't know if y'all know this, but the University of Chicago no longer has a football team. There may be a cause and effect relationship. Though I can't prove it. Okay. And the theory is that we'll put control rods made out of boron, big neutron absorbers, and we'll be able to put uranium in this, and we'll have a controlled nuclear reaction, and we can control it, and it won't blow up. We hope. And that's literally what they were banking. I just think it's like, what if they were wrong? What if they put the first rod of uranium in and went, oh, pull it out, pull it out, pull it out. Sure. And Chicago looks totally different. Right? The Bears would still lose, the Packers, that would change. I'm checking the crowd. It's like, okay, evil looks, they can pick out the Bears fans. But, anyways. So these guys have discovered that they can produce in the process of doing this plutonium. Pu-239. It's not my fault I didn't name it. Okay. Plutonium, they find, is fantastic because unlike uranium-255, which is hard to get, plutonium wants to fission, well, mathematically, 1.7 times, 2 times more often, I'm going to round, than uranium does. This stuff is perfect for a bomb. And on top of that, you can chemically separate it. You don't have to separate out the 1960 pennies. So there are going to, as a result of this, a guy by the name of Lynn T. Seaborn is going to, in Hanford, Washington, develop a plant called the X10 plant, which is literally just a bigger one of these, but it's going to be helium-cooled and near a very large water supply there in Washington, in which they are going to begin producing with this huge carbon pile weapons-grade plutonium. Seaborn actually will take the first samples of plutonium he creates with this, with the X10 plant. He's going to put it in his pocket, hop on a train, go to Chicago so he can show Fermi. Check this out. So our first ever produced weapons-grade plutonium was actually just carried around in some physicist's pocket on a train trip. Just glad that the TSA didn't exist back then. Sir, could you empty your pockets, please? What is this? Can't tell you. So, we now have the means to create 2 different materials of which we can make, theoretically, a bomb of tremendous power. So now we just got to figure out what's the next step. Where are we going to do this? Now, the program to build the first atomic bomb is going to fall on a military representative and a science representative appointed to the project. The military side of things is going to be an engineer by the name of Brigadier General Leslie R. Groves. This guy has 2 things really going for him. Number one, he's a fantastic engineer, which means he can understand a lot of the stuff that they're going to be doing. Number two, he's a fantastic administrator and organizer. Matter of fact, his previous project before being put on the Manhattan Project was he built the Pentagon. Good credentials. J. Robert Oppenheimer is just one of the pioneers and most respected scientists in this new growing nuclear physics field. And also a good motivator and administrator. Though the movie Oppenheimer doesn't really do that much justice. That was one of my problems with that movie. There were some portrayal issues there. So these two men are now going to have to try and decide where are we going to build the facility where we are going to design and construct the first ever atomic weapons. Not technically nuclear weapons, but we'll call them atomics. This is the name of the presentation. Okay. Now they had a lot of places they checked out. It was a spot outside of Los Angeles. Why not there? Reno, Nevada. That'd be a great place, right? We go gambling in the evening. Finally, they settled in. Well, one person even suggests why not Oak Ridge, where we've already built all this other stuff. But finally, they just settled in on two sites, narrowed it down to two sites in New Mexico. It was remote, good for maintaining secrecy, and it had pretty much everything they wanted. And quite frankly, Oppenheimer was very familiar with the area. He'd been there several times. At least times they would go on a sabbatical to clear his head. The first place they were looking at was a place called Jemez Springs. Yeah, it's pronounced Jemez. I used to live there. My wife grew up there. One of the funniest stories I ever heard her tell was when she was talking about these people who were like, we've been going all day looking for Jemez Springs and we can't find it. We keep finding Jemez Springs. So they've been driving up and down State Route 4 all day long. She couldn't tell. I wouldn't either, just because I would have thought it was funny. But Jemez Springs was one of the final candidates, and Oppenheimer liked it. It had a natural hot springs, that was good. But then when he really was looking at it, it's really just a real narrow canyon between two mesas, and it's like, it's just too small. So they settled on an area north, about 25 miles north on the Pajarito Plateau, where there was a camp, the Los Alamos Ranch School for Boys. Boys camp up there. And they thought, oh, okay, well, we'll kick the boys out. And we'll build our facility up there. We'll keep the name. And we'll call it Los Alamos. It'll be a city, but it'll be closed. At least until 1965. You can't get in there without a badge, even if you're just a school kid. So this is going to be the place where they're going to build the massive facilities in which to develop the first atomic weapons. Oppenheimer would later say that the rate of construction at Los Alamos, he said they built it with unbelievable dispatch. Right? The buildings flew up so fast. The houses that they flew up for the workers were called Denver homes because they were prefabricated. There was a whole city block, remember, even on 43rd Street, in which when they put up the wall side for the kitchen, they put the two tack nails to put that wall up and forgot to do the rest of it. And in the 1970s, during windstorms, people were randomly having their kitchen wall fall out of their house. So, now we've got to actually design this thing. Now, we got two designs we're going to come up with, and the two designs are going to be due again with the fact that we're dealing with two separate materials. Uranium-235 is fantastic for fission. It's pretty reliable. And it doesn't really want to do too much, a thing called pre-detonation. Here's the problem you got. You want this stuff to split. You want it to fission, but you don't want it to do it so fast that it fissions faster than the material can get used, and all of a sudden you're just blowing radioactive material. You literally have to time this where all the material is fissioned before this can expand. And you think about that, this is really, really fast, right? Okay. This is a tough thing. Well, uranium's a little bit forgiving when it comes to that. So the design for the bomb they came up with, which was known as the gun-type bomb, will simply take a lump of uranium that is on the edge of critical mass. That's the point where it's just going to start fissioning like crazy. And we'll take another slug of it. We'll put some explosives behind it, and we'll literally just shoot that right down to the other one. Now it's going to hit critical mass, and then boom. And the math said this was going to be incredibly reliable. almost certain to work. Matter of fact, do you know this design, do you know where it was tested first? They want to take a guess. Hiroshima. They knew it was going to work. Plutonium was a different story. With uranium-235, the possibility of pre-detonation with the gun-type design was calculated to be 0.08%. In other words, 8 out of every 10,000 attempts, it's going to blow itself apart. That's pretty exciting. If you put plutonium in the same design, the pre-detonation percentage was calculated to be 94.2%, which means that pretty much 9 times out of 10, this is going to blow itself apart, just create a dirty bomb, not fully react, right? So they had to come up with a different idea. And they said, well, why don't we just do this? If we had a ball of plutonium this size that was just on the edge of being at critical mass, and we just made it this size. Now it is. Just squeeze it. Make it a little bit smaller. That should work. But how do you do that? You surround it with 12 guys, right? You go all on 3. No, that wouldn't work. But, and even if it did, it'd be pretty bad for the guys. Yeah. I don't know the mythical man. I don't think I can get 12 guys now. Right? Because honestly, I'm going like this. This is literally something about this size, about 3 centimeter sphere. Okay. It's not big. Okay. Well, the design they come up with is an implosion device. This is complicated. You take a look at this here. This is actually from an engineering book on the design of the plutonium bomb. This sphere you see here, this little tiny, that's the plutonium. Inside of that, that's a little tiny thing of polonium, which is just a neutron emitter to try and help spike this thing up. All of this is shaped charges, explosives, but explosives that are shaped in cones. You notice that outer, you can kind of see they drew that cone in, so that when they blow up, it all pushes to the center. And then all you got to do is just get them all to blow up at exactly the same time. Because if one blows up early, then it's out the side, right? Like stepping on a ketchup pack. So this they're going to have to test. Somehow or another, just like if we drop this on a city in Japan, we're pretty certain about what we call little boy, right? The gun type design. We'll just go ahead and try that. But this one, there's a good chance that this thing could just fizzle, blow itself apart, make a heck of a mess. Well, that brings us to what we're looking at, the 80th anniversary of today, Trinity. July 16th, 1945. The gadget, they called it, is taken out there to, like I said, it was called Jornada de Muerto, Day of the Dead. It was lava fields out there in the Alabama gunnery range. It was called Trinity because that's what Oppenheimer called it. It was based on one of his favorite poems by a poet named John Donne. Okay. 5:29 a.m. and 45 seconds. They hit T-0. They set this thing off and it worked. Worked perfectly. The flash was incredibly blinding. So much so, in fact, that 90 miles to the north, as the crow flies, if you were in Albuquerque, 5:30 in the morning, walking your dog, probably mad, because why'd your dog get you up at 5:30 in the morning? The sky outside became daytime, not daytime. The sky just turned blue, like it was midday, and then went right back into darkness. Which that had to be unnerving, because think about it, the average citizen doesn't know this is happening. None of this is going on, right? So that must have been pretty unnerving. Enrico Fermi was going around making people's beds. Says, I bet this thing's going to set the atmosphere on fire, and we're going to kill everybody on the planet today. Until finally Leslie Groves walked up to him and said, you're scaring the security guards and the MPs, knock it off. Because they think you're serious. In a way, he kind of was. Who knows? Maybe. Right? Oppenheimer was so taken aback by what he saw. He later said that it reminded him of a line from the Bhagavad Gita in which Vishnu, a Hindu deity, said, "Now I have become death, the destroyer of worlds." Certainly, like I said before, the world will never be the same. Now, I did bring some of that test with me today. That's right. This is green trinitite. This is actual atomic glass that was created from that shot. It's green, not because of uranium. I know we all watch The Simpsons. Oh yeah, uranium shot. First of all. It's green because it actually has trace bits of copper from what copper they did use in the gadget. So I always thought that was going to be the most difficult one to find when full disclosure, when my wife found that, because she's the pro at rocks, not me. But it turns out I was wrong. There's some other color ones that are rare. Do be careful if you ever find yourself in contact with anything like this. This is what it says on the actual box. Do not eat. I'm kidding. Well, I'm sort of kidding. What it says, do not inhale the dust, ingest, so do not eat. Do not rub on your skin or wear as jewelry. Mildly radioactive. Who are they selling this to? Because if it has a warning like that, it's because they had to put it on there. I mean, somebody was going, right? It's like, oh, home chemo. I don't quite understand that. With the result of this test, the little boy, which was a uranium bomb, about the same time as this Trinity shot, had already been transported, or was in the process of being transported, to what was at the time becoming the largest airport on the planet, the airbase in Tinian Island near Saipan, where the B-29s that are going to fly these missions on Japan are going to embark on, including the 509th Composite Squadron, which is going to be the B-29s that actually fly the bomb. This is Paul Tippett's squadron. The little boy was shipped on a cruiser by the name of USS Indianapolis. Indianapolis would become famous later after it's dropped off the parts of the atomic bomb, and on July 30th, 1945, it'll be sunk by a submarine, which many of the sailors will die in the ocean. Some of them succumbing to shark attacks, not to the degree that it's portrayed in the movie Jaws. Oh my goodness, they didn't all get eaten, right? The 50th anniversary of that movie, so of course I had to go write it to watch it again, and it was like, I bought into that when I wasn't a historian. Then I got older, maybe wiser, I don't know. Fat Man, which is going to be the second plutonium bomb, will be shipped out to Tinian shortly thereafter. So, all the pieces are now in place, and now we've got to make a choice. Do we use the bomb? This is something that continues to be controversial even to this day. Matter of fact, I'll go ahead and just take a poll. How many people in here right now, if you're willing, if you don't have to participate in it, say we should not have dropped the bomb? Okay. See, there's opinions on that, right? And if you look at things historically, you see that there's a trend on that. In 1945, Gallup had a poll which they asked Americans that very question: should we use the atomic bomb on Japan? 85% of Americans said absolutely we should have. Right? By 2005, that had dropped down to 57%. The most recent poll I found, which is 2015, which means we're probably due, had it at 56%. That poll actually polled the Japanese people as well. 14% said, yeah, we should have used it. Amazing. That actually surprised me. I expected that to be really close to zero, but it wasn't. The moral implications of using this, we all know, right? We did it. We hold the moniker, as we were reminded by the president of Iran here only just a few weeks ago, we hold the moniker of being the only nation on the planet that has ever dropped an atomic weapon on another country, on their cities. You know, that's just something we've got to live with. But rather than go through and rehash that debate, again, I want to take a different look at it. I want to take a look at it from the perspective of what these men were dealing with at that time, which led them to making that decision. Right? Because ultimately, when we take a look at it, you know, we do know this for a fact. This is historical fact, that the bombing of Hiroshima killed at least 70,000 people immediately, and at least 70,000 people within the next 5 years. If somebody ever gives you an exact number on that, tell them to fold it. There's no way to know. How many people came down with a strange cancer 20 years later that's probably related to it? There's no way of knowing. There was a kite maker that was in Hiroshima, saw that first bomb drop, was like, oh my God, this is crazy. Survived it, went home to his wife in Nagasaki. He said, you won't believe what I saw. And then she said, that? She didn't say that, I'm kind of playing that out there, but you know, because he got there and said he got hit twice. Lived to be in his 90s. I don't know. I don't understand. But we do know that, you know, that the consequences of that are well known. So the question that the leaders, the allies, had to ask themselves in the process of trying to make this decision, do we use this weapon? Is what mechanisms did the Allies have to compel Japan to surrender? This is something they need to think about. Now, I first heard this posed by a historian named John Parshall. Right? He discussed this. And it really got me thinking about that. Right? What mechanisms did the Allies have to compel Japan to surrender? Well, there's a lot of different directions we can think about that. We can say, well, maybe just the existence of the atomic bomb would that do it? That compelled us to say, hey, we got to quit. Could it be the fact that their army, their navy was certainly defeated, but their army was also on the brink of collapse? What about their infrastructure? The Japanese knew full well that in 1946 they were going to have mass famine in Japan, mass starvation, because their entire infrastructure had broken down. They couldn't even get food to their own people. What would compel them? Well, the answer to that question, generally, is there's nothing that the United States would have had in their arsenal that would have done that. The only thing to compel Japan to quit would have been for the peace to finally, for in their headspace, the peace has to be better than staying at war. That is ultimately where they needed to get to. There's nothing that we as the Allies could have done in order to get them there. All we could do is try with what we had to see if we could get their headspace into our headspace. Our headspace was, you guys are beaten. You need to stop. Enough people have died. Now, one of the reasons that we don't tend to think about this, and when we think about the moral issues of the atomic bomb, one of the reasons why we head down that path is that we have this tendency to think about the use of the atomic bomb in terms of American lives saved versus Japanese killed. So we need to broaden that out a little bit more. We need to think a little bit wider on that. Now, granted, the reality of the situation was that as the war was going on, it was getting bloodier and bloodier and bloodier in the Pacific. These conflicts that they were having in 1943 in Tarawa, right, on the beginning of the island hopping campaign, you have, these are casualties. Remember, casualty doesn't mean dead. Casualty just means cannot fight. It does include dead, but it also means wounded, POWs, captured, lost. Right? 3,800 casualties for the United States, 4,700 for the Japanese, of which really, honestly, I'm putting rounded numbers on there. I could get a little bit more exact, but I won't, right? Because again, there's always that little bit of fuzziness with these numbers. Of that 4,700, though, only 17 lived. Right? The Japanese wouldn't quit. 17 captured, that was it. 17 surrendered technically, 7 surrendered, 10 captured, because 10 of those that surrendered were unconscious at the time. Japan, 1944, June and July. U.S. casualties, 26,000. Japanese casualties, 23,000. Again, most of them dead, except about 1,800. U.S. forces had about 5,000 dead out of that 26,000. 22,000 civilian casualties that were either murdered, killed by being caught in the line of fire, pushed out in front of advancing Japanese columns, or committed mass suicide. Okay. Okinawa, beginning in April 1945. See, it keeps going up. 49,200 American casualties, 110,000 Japanese casualties. Again, most of them dead. In this case, you only have, I think, did I not write it down? I didn't write it down. Somewhere around 5,000 captured out of that. At least 100,000 civilian casualties. Again, the same thing. Caught in the line of fire, killed, etc., mass suicide. Okay. At the same time, during this attack, Japanese kamikazes sunk 26 U.S. naval vessels, damaged 168 more. Both commanding officers on both the Japanese side and the American side were killed in action, while the Japanese commander actually committed seppuku, ritual suicide. Okay. Approximately 25% at least of the civilian population of Okinawa was killed. That is that, again, American lives versus Japanese life perspective of it. But expanding out on that, not all casualties were on the front line. During the war, China lost somewhere between 15 and 22 million people. Indochina lost between 1 and 2 million people. Most of them in 1944 and 1945 due to famine that had set in by the end of 1944. Same thing goes for Indonesia, specifically the island of Java, ultimately leading to somewhere between 2 and 4 million deaths on these islands. These are separated out from the American casualties and the Japanese casualties. By 1945, Americans were losing about 10,000 men a month in casualties, in deaths. The Japanese were losing 38,000 soldiers and about 82,000 civilians dead per month. But China's losing 48,000 soldiers and 233,000 civilians dead per month. Every month this war goes on. And collectively, the rest of Asia, another 300,000 dead per month. There's a vested interest to end this war as quickly as possible. As a result, these planners had to come up with one of 3 choices. One was a blockade. And they were already doing it. Japan was pretty much cordoned off. Right? That's a cheap and easy one to do, right? We just blockade it, we wait them out, and eventually they got to quit, right? We got nothing left. Okay. The second choice is invade Japan, which we were building a plan to do. It was called Operation Downfall, consisted of 2 invasions, one of the island of Kyushu, known as Operation Olympic, and the other one was the island of Operation Coronet, which would be the invasion of Honshu. The whole idea is that we get Kyushu because we need air bases, because we want an aircraft carrier you can't sink. We can't sink an island, right? So that we move to the next. The entire Pacific campaign is all about air bases. And of course, the third choice is to use the atomic bomb, the hope that you have taken that step to compel them to quit. So, take a quick look at both of these. I want to make sure I wrap this up in time, as I said. The blockade of Japan, as I kind of touched on before, the food situation for 1946 was already looking dire. The Japanese had been completely isolated by 1945. The prospect of getting material into Japan from Korea, China, and elsewhere had become harder and harder. The bulk of their merchant fleet had been sunk. The bulk of their coastal transportation, just island to island, had been destroyed, which was actually, they used that more than they used the railroads. Their railroads were also, though, coming under attack. Matter of fact, it was estimated in September of 1945, at the time of the surrender, that the Americans were 2 weeks away from completely obliterating the railroads in Japan. Every choke point, every hub, every tunnel destroyed by that time. Okay? Japanese sources in that time period stated that they expected to have somewhere between 5 and 10 million deaths due to famine in 1946. And I think that's supported by the fact that after the occupation in September of 1945, the United States will commence by the summer of 1946 to bring 800,000 tons of food into Japan. Food and other humanitarian aid. 800,000 tons. Right? So that's a large loss of life for a war that would probably go on at least until April, May, we're assuming like 8 months until next year. The second option is not much more attractive. Invade Japan. We had taken Okinawa. The next logical place was to take Kyushu. We knew that. Guess who else knew that? The Japanese. Now we had a plan. That Operation Olympic made a lot of sense. We're going to send about 750,000 men. 766,000 men will land on that island. In January 1945, there's only about 350,000 Japanese soldiers on this island. 3-to-1 odds, it's about what you want on a beach landing. It's to outnumber them 3-to-1. But because the Japanese did know about that, by July of 1945, it's estimated that they had over 900,000 troops on Kyushu. And 10,000 aircraft at the ready, with the shortage of fuel mostly to be used as kamikazes. The plan that the Japanese had to try and defend those beaches in Kyushu was called Tetsugo. They had a commanding officer that was organizing the entire thing. In March of 1945, they passed an ordinance called the National Labor Service Mobilization Ordinance. This ordinance stated that every able-bodied man and woman in Japan is now a military auxiliary that is attached to whichever local Imperial Army unit that is in your neighborhood. Blanket conscription. Didn't matter who you were, they were going to start training you, mostly with bamboo sticks. So as the Americans were looking at the prospect of landing on Kyushu, they were also looking at they know this stuff, they were looking at the prospect of possibly having groups of civilians come at them. You don't know if they're surrendering to you or are they about to try and run you through, try and kill you. What do you do? What are your choices? There's 12.6 million civilians on this island in 1945. If we use just the numbers from Okinawa, 25%, that's 4 million civilians killed in just that one invasion. It's a huge number, right? Something they had to think about. And then, of course, the last option was dropping the bomb, seeing if that would be the final spark to entice Japan to surrender. Now, like I said, we know what the decision is. We did not. Operation Downfall never happened. Olympic, Coronet, never happened. The blockade, of course, ended once the surrender happened. That was ongoing. Remember, these things weren't mutually exclusive. If we were invading Kyushu, we would still be blockading. Lamaine would still be firebombing cities. None of that would have changed. Right? Okay. We chose that. Now, Truman made this decision. Did he make this decision based off of all this stuff I just said about all these civilians in China and Indochina? No, he didn't. No, he was thinking about the American lives versus Japanese deaths. That same thing that gets us kind of stuck on that, and that moral dilemma still to this day. Right? We do get hung up on that. And Truman definitely was his motivation was simply end the war quickly as possible. If I have a weapon that can end the war as quickly as possible, if it works and does that, then I've justified using it. If I don't use it and it goes longer, how do I start that conversation with that Blue Star mom that just became a Gold Star mom? And then they find out I had a weapon that reminded it and it kept their kid alive. How do you start that conversation? Right? These are the things Truman was thinking about. Not whether or not he was going to save Japanese lives. Just being clear about it. Okay? But the reality is that all these lives weren't lost ultimately, because this did ultimately end the war. There's a little bit more to it than that. Nothing has one reason. If I get hit with a baseball bat, one of the reasons why is I didn't duck. But there was probably something that compelled that person trying to hit me with a baseball bat. I guarantee it was probably something I said. Right? And I almost 100% guarantee it was my sense of humor. So the green light is given on August 6th, 1945. Little boy was dropped on Hiroshima. Worked as advertised, right? This is where they were testing it for the first time. And like I said, the general numbers that we put out there is 70,000 killed immediately, another 70,000 within 5 years. And you'll hear numbers all over the map on that. But just know, it's a large number of people in a very short amount of time. 3 days later, we dropped Fat Boy, the plutonium bomb on Nagasaki. The idea behind this, again, because of the geography, 70,000 killed there, and that's relatively a lower number, but it's the geography that really dictated that. Coast side, it's kind of been a bowl. A lot of the forces go out into the sea. Okay. The next bomb that wasn't going to be available until at earliest August 18th. But the impression that they were trying to give the Japanese by dropping them 3 days apart was that we can do this every 3 days forever. Again, remember, we're trying to compel them that the peace is better than staying at war. Did it have an effect? Yeah, it did. According to notes from the Diet, right, this is the Japanese parliament, there was already talk about trying to find a way out of the war. The emperor had already made his wishes known in June of 1945 that he wanted to find an exit. Ambassador Sato, who was the Japanese ambassador to the Soviet Union, had been ordered by the foreign minister, Togo, to get the Russians talking to them to talk about a negotiated settlement. Okay. According to the notes captured after the bombing of Hiroshima, there was a sense of urgency after that. So we got to get the Russians talking to us now. It was strange. They said, well, there's a bomb, destroyed the city. We got to get the Russians talking to us. They did very little talking about the bomb itself. Except for some of the militarists that said, I don't think it's real. Hiroshima just disappeared on its own. It blew itself up. I don't know what to think. After Nagasaki, at the same time, the day before that, Russia declared war on Japan, and pretty much at that point they know it's over. So I would argue collectively, between the atomic bomb and the Russian declaration of war, we finally hit that threshold where Japan realized, okay, peace is worth having. Peace, we found that threshold to compel us, right? Even then, it's not a sure thing, right? Emperor Hirohito, the show-off emperor, one of his biggest worries about is what happens when the surrender happens, mostly because of the Potsdam Declaration. In Casablanca in 1943, President Roosevelt shocked everybody when he suddenly just out of the blue announced we are going to accept from Germany nothing but unconditional surrender. We want the Germans to know they've been defeated. And that was definitely something based on World War I that needed to happen. Right? But even Churchill was like, oh, bro, you didn't even ask me. Right? But it stuck. Well, the Potsdam Declaration is going to make the same demand of the Japanese, but it's a different culture. It's a different mindset. And so one of the problems with that, with Germany, when they, of course, surrendered, they were occupied. Their leaders that had survived anyways were put on war crime charges, right, with the trials there in Nuremberg. With Japan, that's hard when you take a look at your emperor. He could be put on war crime charges. He could be executed. But in Japanese culture, this is a living God. At this time, the belief is that the emperor was the living descendant of Amaterasu Omikami, the goddess of the sun. This is a living deity. Think about this for a second. If by you quitting something could mean that your God gets killed by your adversary, are you going to be motivated to quit? Or might you keep going? So, I mean, it's a tough sell. When the Potsdam Declaration came out, Togo contacted Sato. This is just a few days before Russia declared war. And said, what are we going to do in order to get Russia to start talking to us? And Sato replied in a telegram that was coded with their diplomatic code, what we call purple. It said, the only way I can see us in the war is that we say we accept the Potsdam Declaration under the one condition that the emperor is preserved and kept safe. Togo responded in the coded message, says that is absolutely unacceptable. We will never do that. Now here's the problem with that. These are two coded messages that went back and forth. We broke their code back before Pearl Harbor, their diplomatic code. We were reading their mail. We knew this. We decoded that. There's always this talk about that, the mistranslation, to the Potsdam Declaration that the Japanese intentionally ignored, but it was a mistake. None of that matters because there were actually some direct messages. The United States knew that that wasn't on the table for them. All right? It wasn't until the emperor finally actually stood up on August 9th and gave what was called the Go Sit Down, the sacred decision, in which he said, according to Minister Hoshino, said, I have no expectations for victory after considering our material power compared to the enemies in various situations in and out of the country. I should bear the unbearable from the broader perspective. So I decided this way in order to save the people from disaster and bring about happiness to mankind around the world. The emperor saying, okay, we need to do that. And even that may not be enough. Matter of fact, on August 14th, the emperor reported a message that was going to be broadcast to the people of Japan. And there was actually an attempt by Japanese soldiers to intercept that record to make sure it wouldn't get played across the radio. They went to the Imperial Palace, went to the head of the Imperial Guard, a guy that way outranked him, and said, will you join us and help us find this record? He said, no, I'm going to obey the emperor. So they killed him. Right? It's called a Gekukujo. Actually, subordinates kill the superiors in order to make sure they get them. They ultimately didn't find it. The message was broadcast on the 15th. In that message, he does talk about this, as he put it, a new and most cruel bomb, the power of which the damage is indeed incalculable. He says it would only be the result in an ultimate collapse and obliteration of the Japanese nation should we continue to fight. Once the people hear this, now the surrender is inevitable. Right? And by September 2nd, this has happened. So, that kind of sums up, this was what these guys were having to deal with at that time to make that decision. So whether or not we approve of it today, these were the options that they had available to them. I personally feel, like I said, you don't have to agree with me, that ultimately it saved a lot of lives. That doesn't mean that I would agree to using it ever again. Because it's a case where every option is bad. Take a look at those three options, none of them are good. Right? At that time, that place, in that instance, it was just one that was the lesser of the three evils, I guess. So, anyways, I put this on here just so if there's any further reading anybody wants to do. That's just a few of the sources that I use for this. Very tiny print. This is just some of the stuff I know, and actually it's about half the stuff I know because I'm a hoarder.